light is perhaps the most familiar phenomenon in the universe, and simultaneously one of the most resistant to complete understanding, a subject that has occupied philosophers, theologians, natural philosophers, physicists, engineers and biologists across every recorded civilization, each generation believing it had finally grasped the essential nature of illumination, only to discover that deeper questions awaited beneath the surface of apparent knowledge. The history of human engagement with light is not simply a chronicle of scientific discovery, but rather a complex interweaving of technological development, economic transformation, social reorganization, and fundamental shifts in how human beings conceptualize their relationship to the natural world. And tracing this history reveals patterns of causation and consequence that were rarely apparent to those living through them. The earliest human encounters with light beyond the daily cycle of sun and darkness came through fire, and the control of fire represents one of the most significant technological transitions in the entirety of human existence, though dating this transition precisely remains a matter of considerable scholarly debate. Archaeological evidence from sites in South Africa, particularly Wonderwerk Cave, suggests controlled fire use extending back approximately 1 million years, while other researchers argue for more conservative estimates, placing reliable fire control at roughly 400,000 years before the present. The distinction matters because fire control fundamentally altered not only immediate physical circumstances, but the entire trajectory of human biological and social evolution, enabling cooking which increased caloric availability and may have contributed to encephalization, extending productive hours into darkness which allowed for new forms of social interaction and knowledge transmission, and providing protection from predators which permitted settlement patterns otherwise impossible. The light of fire was never merely illumination, but always carried these deeper implications for human organization and development. Ancient Mediterranean civilizations developed sophisticated oil lamp technologies that remained fundamentally unchanged for millennia, using clay or metal vessels to contain olive oil or other combustible liquids with wicks typically made from plant fibers. The Roman period saw mass production of terracotta lamps in standardized forms, with archaeological evidence from sites like Pompeii revealing the ubiquity of artificial lighting in urban, domestic and commercial contexts, though the quality and intensity of this light remained poor by later standards, providing perhaps the equivalent of a few modern candles per lamp and requiring constant maintenance of wicks and fuel supplies. Economic historians have attempted to calculate the cost of artificial light in antiquity relative to wages, and the results suggest that sustained artificial illumination represented a substantial expense for most households, constraining the activities that could practically occur after sunset to those of sufficient value to justify the fuel consumption. This economic constraint on light availability shaped patterns of daily life, labour organisation, and social interaction in ways that persisted until relatively recent centuries. The relationship between light and religious thought developed along parallel tracks in multiple civilizations without obvious mutual influence, suggesting something about the fundamental cognitive associations humans form between visibility, knowledge, and transcendence. Zoroastrian traditions dating to at least the first millennium before the Common Era placed fire and its light at the center of ritual practice and cosmological understanding, conceptualizing existence as a cosmic struggle between light and darkness, with explicit moral valence assigned to each. Egyptian religious iconography centered solar imagery as a manifestation of divine presence, with the sun god Ra traversing the sky in a boat and descending to the underworld each night, in a cycle of death and renewal that structured both religious practice and calendrical organization. Greek philosophical traditions, beginning at least with Plato, employed light as a central metaphor for understanding and truth, most famously in the allegory of the cave where prisoners mistake shadows for reality until one escapes to perceive objects in actual sunlight, a metaphor that has proved remarkably persistent in Western thought, despite or perhaps because of its ambiguities. The physics of light as understood in the ancient world remained largely qualitative and speculative, with competing schools of thought proposing fundamentally incompatible mechanisms for vision and illumination. The emission theory, associated with thinkers including Empedocles and later Plato, proposed that vision resulted from rays emanating from the eye and touching objects, which raised obvious difficulties explaining how distant stars could be seen if eye rays had to travel such distances. The intromission theory, which would eventually prove closer to modern understanding, proposed that objects emitted something that travelled to the eye. But the mechanism of this emission remained unclear, and the theory struggled to explain certain optical phenomena, including the apparent sizes of objects at varying distances. Aristotle proposed that light represented a change in the state of a transparent medium rather than the transmission of substance, an insight that contained elements later developed in wave theories, though embedded in a conceptual framework quite different from modern physics. Islamic scholars working primarily between the 9th and 11th centuries of the Common Era made contributions to optics that remained unsurpassed in systematic rigour until the 17th century. With Ibn al-Haytham's Kitab al-Manazir, composed around 1011 and later translated into Latin as Dia Spectibus or Perspectiva, representing a particularly significant achievement. Ibn al-Haytham conducted what might be called experimental investigations of reflection and refraction, developing mathematical descriptions of ray behaviour and constructing arguments against emission theories of vision based on the physical implausibility of eye rays reaching distant celestial objects instantaneously. His work on the camera obscura, describing how images formed when light passed through small apertures, demonstrated principles that would later prove essential for understanding both the eye and optical instruments, though the technological exploitation of these principles remained limited for centuries. The transmission of this knowledge to medieval European scholars occurred through complex pathways involving translation centres in Toledo and elsewhere, and the integration of Arabic optical learning into scholastic natural philosophy required conceptual adjustments on both sides. Medieval European understanding of light developed within theological frameworks that assigned cosmic significance to illumination, most explicitly in the light metaphysics associated with Robert Grosseteste and his intellectual successors in 13th century Oxford. Grosseteste proposed that light was the first form created by God and that it possessed unique properties allowing it to propagate itself and generate spatial extension, making light quite literally the foundation of physical reality in ways that anticipated much later theories, though embedded in purposes quite different from modern physics. This theological interest in light connected with practical concerns about illumination in ecclesiastical architecture, where the development of Gothic construction techniques, allowing larger window areas, enabled the creation of interior spaces flooded with natural light filtered through stained glass, producing effects understood as spiritually meaningful rather than merely aesthetic. The economic resources required for such construction were substantial, and the chronology of Gothic cathedral building correlates with periods of agricultural surplus and commercial expansion in northern France and surrounding regions. The development of spectacles for correcting vision, emerging in northern Italy during the late 13th century, represented a practical application of optical knowledge that would have significant though gradual social and economic consequences. The earliest clear documentary references date to the 1280s and 1290s, with production centred initially in Venice and Florence where glassmaking expertise concentrated, and the technology spread across Europe over the following centuries with varying rates of adoption dependent on literacy levels, economic development, and craft traditions. Spectacles extended the productive working lives of scholars, scribes, and craftspeople whose occupations required close visual work, and quantifying this effect remains difficult, but the implications for knowledge production and skilled labour availability were likely considerable. The grinding of lenses required precision craftsmanship that would eventually contribute to the development of more sophisticated optical instruments, creating a pathway from corrective eyewear to telescopes and microscopes, though this pathway took centuries to traverse. The 16th and early 17th centuries saw the emergence of new optical instruments that fundamentally transformed human perceptual capabilities, with the telescope conventionally dated to 1608 based on Dutch patent applications, though the conceptual foundations had been developing for decades prior. Galileo's observations with improved telescopes beginning in 1609 revealed phenomena that challenged prevailing cosmological frameworks, including lunar surface irregularities, Jupiter's satellites, and the phases of Venus, each observation carrying implications for the structure of the cosmos and the reliability of human sensory access to astronomical truth. The microscope developed along parallel timelines, with early compound instruments appearing by the 1590s, though the resolution and clarity remained limited until later improvements, and the revelation of previously invisible worlds of small organisms and structures raised philosophical questions about the completeness of ordinary perception. These instruments did not merely extend existing senses, but raised questions about what other phenomena might exist beyond current instrumental capabilities, a question that has recurred with each subsequent expansion of observational technology. The controversy between wave and particle theories of light that would dominate optical physics for centuries took more systematic form in the 17th century, with Christian Huygens articulating wave-based explanations, while Isaac Newton favoured corpuscular interpretations. Huygens's wave theory, presented in his treatise on light composed in the 1670s though published later, successfully explained reflection and refraction through the behaviour of wave fronts encountering surfaces, and his construction for predicting refracted ray directions remains mathematically valid, though the underlying model has been substantially revised. Newton's corpuscular theory, developed in his Optics published in 1704 though based on decades of prior investigation, conceived light as streams of particles whose behaviour could explain reflection straightforwardly and refraction through assumptions about particle velocities in different media. The experimental evidence available at the time could not definitively distinguish between these theories, and Newton's immense authority ensured that corpuscular interpretations remained influential, particularly in British natural philosophy well into the 18th century. Newton's investigations of colour through prism experiments, conducted initially in the 1660s, demonstrated that white light comprised a spectrum of colours that could be separated and recombined, challenging earlier theories that conceived colours as modifications of pure white light rather than components of it. The systematic character of the spectrum, with colours appearing in consistent order, and each corresponding to what Newton termed a particular degree of refrangibility, suggested underlying regularities amenable to mathematical description, though the physical basis of these differences remained unclear within the conceptual resources available. The distinction between spectral colours, each corresponding to a particular refrangibility, and compound colours produced by mixing, provided a framework for understanding colour phenomena that would be extended and complicated by later research into colour perception, dye chemistry, and eventually electromagnetic theory. The measurement of the speed of light, first accomplished with reasonable accuracy by Ole Römer in 1656 through astronomical observations of Jupiter's satellite Io, provided quantitative data that would prove essential for later theoretical developments, though its immediate implications were less clear. Römer observed that the timing of Io's eclipses varied systematically with Earth's orbital position, and he correctly attributed this variation to the finite time required for light to traverse the varying distance between Earth and Jupiter, calculating a speed that was within the correct order of magnitude, though subject to considerable uncertainty given the astronomical data available. This finding contradicted assumptions, associated with Descartes among others, that light propagation was instantaneous, and it raised questions about how any physical mechanism could produce such enormous velocities, questions that would not receive satisfactory answers until 19th century electromagnetic theory. 18th century developments in lighting technology, while modest compared to later transformations, nevertheless produced measurable improvements in artificial illumination and its availability. The argand lamp, invented by Aimé Argand in 1780, incorporated a cylindrical wick and glass chimney that provided improved combustion and substantially increased light output compared to traditional oil lamps, representing perhaps the most significant improvement in oil lamp technology since antiquity. The economics of artificial lighting began to shift as industrial development proceeded, with whale oil prices fluctuating based on hunting success and demand patterns, and the search for alternative illuminants including various plant and mineral oils intensified. The relationship between lighting availability and urban social life became increasingly apparent to contemporary observers, with improved street lighting in major European cities correlating with changes in patterns of nighttime activity, commerce, and social interaction, though establishing clear causal relationships remains methodologically challenging. The wave theory of light received decisive experimental support in the early 19th century through the work of Thomas Young and Augustin Jean Fresnel, whose demonstrations of interference and diffraction phenomena could not be explained by corpuscular theories without elaborate and unconvincing auxiliary hypotheses. Young's double-slit experiment, first described in 1801, showed that light passing through two narrow adjacent slits produced interference patterns on a screen, with bands of constructive and destructive combination exactly as predicted by wave behaviour, and this result essentially settled the wave-particle debate for most of the 19th century. Fresnel developed mathematical descriptions of diffraction that allowed precise quantitative predictions of light behaviour at edges and apertures, providing the wave theory with predictive power that corpuscular alternatives could not match, and his work on polarization revealed additional properties of light waves that carried implications for understanding the medium in which these waves propagated. The concept of the luminiferous ether, the hypothetical medium required to support light wave propagation, became increasingly problematic as physicists attempted to specify its properties with sufficient precision to account for observed optical phenomena. The ether needed to be rigid enough to support the extremely high-frequency transverse vibrations implied by light's properties, yet sufficiently fluid to allow celestial bodies to pass through it without detectable resistance, and these requirements seemed contradictory within the framework of ordinary mechanics. Various proposals for ether structure accumulated through the 19th century, each addressing certain problems while creating others, and the theoretical situation became increasingly uncomfortable, even as optical technology advanced, and spectroscopic techniques revealed new phenomena requiring explanation. This tension would eventually be resolved not by discovering the correct ether model, but by abandoning the ether concept entirely, though this resolution lay decades in the future and could not have been anticipated by researchers working within the prevailing conceptual framework. The development of gaslighting beginning in the early 19th century transformed urban environments and daily life patterns in ways that contemporaries recognized as revolutionary, though they could not fully anticipate the long-term consequences. William Murdoch's installation of gaslighting at the Bolton and Watt factory in Birmingham in 1802 demonstrated the technology's commercial potential, and the establishment of the Gaslight and Coke Company in London in 1812 began the process of systematic urban illumination. Gas distribution required substantial infrastructure investment in pipes, storage facilities, and manufacturing plants, creating natural monopoly conditions that led to franchise systems and eventually municipal ownership in many jurisdictions. Establishing regulatory patterns that would later apply to electrical utilities, the quality of gaslight exceeded anything previously available to most urban residents, and the extension of productive and social hours into darkness accelerated industrial work patterns while transforming entertainment, commerce, and public safety in city centres. The relationship between gaslighting and labour discipline received attention from contemporary social observers and has been extensively analysed by historians, with the technology enabling factory work schedules that extended beyond natural daylight hours and contributed to the intensification of industrial labour. The timing of these developments varied substantially across regions depending on urbanisation rates, coal availability, and capital investment patterns, with British cities generally leading while continental European and American adoption followed with various delays. The cost of gaslight declined substantially over the decades following initial introduction as manufacturing processes improved and distribution networks expanded, making artificial lighting accessible to broader segments of urban populations and contributing to what some historians have termed the colonisation of the night. Environmental consequences of gas production, including toxic byproducts and explosion hazards, became apparent through experience and led to evolving safety regulations, though comprehensive understanding of these issues developed only gradually. The scientific understanding of light underwent fundamental transformation in the 1860s, through James Clerk Maxwell's theoretical work demonstrating that light was an electromagnetic phenomenon, a result that unified previously separate domains of physics and predicted the existence of electromagnetic waves at frequencies beyond the visible spectrum. Maxwell's equations, developed through the 1850s and 1860s, provided a complete mathematical description of electric and magnetic field behaviour, and from these equations Maxwell derived that electromagnetic disturbances would propagate at a velocity that matched, within experimental uncertainty, the measured speed of light. This was not merely a coincidence of numbers, but implied that light waves were electromagnetic waves, a proposal that carried revolutionary implications for understanding both optics and electromagnetism, while raising new questions about the ether that supposedly carried these waves. The experimental verification of Maxwell's predictions by Heinrich Hertz in the late 1880s, demonstrating radio wave generation and detection, confirmed the theoretical framework and opened pathways toward wireless communication technologies. The development of spectroscopy as a quantitative analytical technique revealed the relationships between light and matter with unprecedented precision, demonstrating that each chemical element produced characteristic spectral lines when heated to incandescence. Gustav Kirchhoff and Robert Bunsen's systematic investigation of spectral signatures beginning in 1859 established spectroscopy as a tool for chemical analysis and for determining the composition of distant astronomical objects whose light could be analysed. The discovery of helium through solar spectroscopy in 1868, detecting spectral lines that matched no known terrestrial element, demonstrated dramatically that this technique could reveal the presence of substances not yet isolated on Earth, and helium was eventually identified in terrestrial samples decades later. The patterns of spectral lines for each element, while distinctive enough for identification purposes, followed regularities that existing physical theories could not explain, and the search for underlying principles governing these patterns would eventually contribute to quantum theory. The practical development of electric lighting proceeded through multiple competing approaches during the 1870s and 1880s, with the arc lighting providing high-intensity illumination suitable for street lighting and large spaces, while incandescent lamps proved more appropriate for domestic and commercial interior applications. The incandescent lamp, as developed by Thomas Edison and his collaborators at Menlo Park, required not merely the invention of a suitable filament, but the creation of an entire system, including generators, distribution networks, metering devices, and associated infrastructure. Edison's Pearl Street Station in New York, commencing operation in 1882, represented the first commercial central power station, though the rapid expansion of electrical systems would eventually be dominated by alternating current systems despite Edison's opposition. The transition from gas to electric lighting occurred over decades rather than years, with gas companies adapting by improving their technology, reducing prices, and finding new applications, and complete displacement of gas lighting did not occur until well into the 20th century in many areas. The economic implications of electrical lighting extended far beyond simple substitution for previous illumination sources, affecting industrial organization, urban planning, and patterns of daily life in ways that contemporaries only partially recognized. Electrical lighting separated illumination from combustion for the first time, eliminating fire hazards associated with candles, oil lamps, and gas fixtures, and reducing heat output, which had significant implications for comfort and air quality in enclosed spaces. The reliability and controllability of electric light enabled new forms of factory organization, retail display, and entertainment, with department stores, theaters, and eventually cinema exploiting the technology's possibilities. The infrastructure required for electrical distribution created new industries, employment patterns, and regulatory challenges, while the visibility of electrical systems became markers of modernity and development with significant political and cultural dimensions. The crisis in classical physics that would lead to quantum theory emerged partly from investigations of the relationship between light and matter, specifically the problem of black body radiation, which described the spectrum of light emitted by heated objects. Classical electromagnetic theory predicted that a perfect absorber, an emitter of radiation, a so-called black body, should emit radiation following a particular spectral distribution. But the predicted distribution diverged catastrophically from observation at high frequencies, implying infinite total radiated energy in what became known as the ultraviolet catastrophe. Max Planck's resolution of this problem in 1900, introducing the hypothesis that energy was emitted and absorbed in discrete quanta proportional to frequency, provided accurate predictions but at the cost of assumptions that seemed incompatible with classical physics, and Planck himself remained uncertain about the physical significance of his mathematical device. The quantum hypothesis proved essential for understanding the photoelectric effect, in which light-ejecting electrons from metal surfaces displayed characteristics that wave theories could not explain, but which Einstein successfully analysed in 1905 using light quanta, later termed photons. The concept of wave-particle duality that emerged from early 20th century physics represented a fundamental departure from classical intuitions about the nature of physical reality, and light became the primary example through which this counterintuitive behaviour was discussed and debated. Light exhibited interference and diffraction, exactly as expected for waves, yet also displayed particle-like properties in interactions with matter, and no classical model could simultaneously accommodate both aspects of behaviour. The development of quantum mechanics through the 1920s provided a mathematical framework for handling this duality, but the interpretive questions about what the mathematical formalism meant for the underlying nature of reality remained contested among the theory's founders and continue to generate philosophical discussion. The practical success of quantum electrodynamics in predicting electromagnetic phenomena to extraordinary precision did not resolve these interpretive debates, demonstrating that predictive adequacy and conceptual clarity need not coincide. The discovery of the electromagnetic spectrum's extent beyond visible light opened entire new domains of scientific investigation and eventually technological application, with each spectral region revealing different aspects of physical reality and enabling different practical capabilities. Infrared radiation, discovered by William Herschel in 1800 through temperature measurements beyond the red end of the visible spectrum, would eventually enable thermal imaging, remote sensing, and communications technologies. Ultraviolet radiation, detected by Johann Ritter shortly after, proved important for understanding photochemistry and would later become relevant for sterilization, fluorescent lighting, and understanding the health effects of solar exposure. The discovery of X-rays by Wilhelm Röntgen in 1895 and gamma rays through studies of radioactivity shortly after extended the spectrum to very high frequencies with distinctive interaction properties that would prove medically and industrially significant. The development of radio communication in the decades following Hertz's experimental demonstration of electromagnetic waves created new industries, transformed military and maritime operations, and eventually reshaped mass culture in ways that exceeded what early researchers and inventors anticipated. Guglielmo Marconi's commercial development of wireless telegraphy beginning in the 1890s depended not only on technical innovations but on securing capital, establishing regulatory frameworks, and creating the infrastructure required for reliable service. The transition from point-to-point wireless telegraphy to broadcasting emerged through multiple pathways in different countries, shaped by existing telecommunications policies, commercial interests, and governmental preferences regarding spectrum allocation and content regulation. The cultural and political implications of broadcasting received extensive contemporary analysis, and the medium's capacity for either democratic communication or propagandistic manipulation became apparent through experiences in the interwar period. The physics of light played a central role in the development of special relativity, with Einstein's 1905 paper famously based on two postulates: the principle of relativity requiring that physical laws take the same form in all inertial reference frames, and the constancy of the speed of light in vacuum regardless of the motion of source or observer. The second postulate implied the failure of classical concepts of absolute time and space, requiring instead that measurements of length and duration depend on the relative motion of observer and observed, consequences that seemed paradoxical but which followed necessarily from the postulates and were subsequently confirmed experimentally. The light speed limit on the transmission of information and causal influence became a fundamental feature of relativistic physics, constraining possible physical processes and contributing to the framework within which cosmology and high-energy physics would develop. The relationship between light speed and the structure of space-time went beyond mere limitation, with general relativity later describing how mass and energy curved space-time itself, affecting the paths of light rays and producing phenomena including gravitational lensing. The practical application of new light sources and illumination technologies continued through the 20th century, with fluorescent lighting emerging in commercially viable form in the late 1930s and eventually dominating many commercial and industrial applications due to its greater efficiency compared to incandescent lamps. Fluorescent lamps operated on different physical principles than incandescent bulbs, using electrical discharge in gas-filled tubes to produce ultraviolet radiation that excited fluorescent coatings to emit visible light, and the efficiency advantages reflected fundamental differences in energy conversion mechanisms. The colour characteristics of fluorescent light differed from incandescent sources in ways that affected colour perception, and had implications for applications where colour accuracy mattered, leading to ongoing development of phosphor formulations and lamp designs. The environmental implications of fluorescent technology included both benefits from reduced energy consumption and concerns about mercury content requiring appropriate disposal procedures. The invention of the laser in 1960 created a qualitatively new type of light source with properties that enabled applications impossible with conventional illumination, including coherence, monochromaticity, and the ability to focus energy with extraordinary precision. Theodore Maimann's demonstration of the first working laser used a ruby crystal as the gain medium, and subsequent developments rapidly expanded the range of available laser types, operating at different wavelengths and power levels. Initial laser applications included precision measurement, material processing, and optical communications research, and the technology proved essential for developments including compact disc audio storage, fiber optic telecommunications, and laser surgery. The physical principles underlying laser operation, involving stimulated emission as predicted by Einstein's 1917 analysis of radiative processes, illustrated how theoretical insights could eventually enable transformative technologies, though the pathways were rarely direct or predictable. Fiber optic communications transformed the infrastructure of global telecommunications beginning in the 1970s, with the development of low-loss optical fibers enabling light-based data transmission over distances that expanded progressively as materials and technologies improved. The capacity advantages of fiber optic systems over electrical transmission reflected fundamental physical differences, with the high frequency of optical carriers permitting vastly greater bandwidth than radio or microwave systems. The installation of transoceanic fiber cables in the 1980s and subsequent expansion of fiber infrastructure contributed to the acceleration of global communications that characterized the late 20th century, though the relationship between technological capacity and actual communication patterns reflected social and economic factors as much as pure technical capability. The continuing development of optical communications, including wavelength division, multiplexing, and increasingly sophisticated modulation schemes, has maintained steady increases in transmission capacity that show no signs of approaching fundamental limits. The role of light in biological systems extends far beyond vision to include fundamental processes in energy, metabolism, developmental regulation, and behavioral timing, with photosynthesis representing perhaps the most consequential biological interaction with light. The capture of solar energy by photosynthetic organisms and its conversion into chemical energy stored in organic compounds provides the energetic foundation for nearly all terrestrial ecosystems, with the exceptions of chemosynthetic communities at hydrothermal vents and similar environments. The evolution of oxygenic photosynthesis, probably occurring around 2.7 billion years ago based on geological evidence, transformed Earth's atmosphere and enabled the subsequent evolution of aerobic metabolism and multicellular life. The molecular mechanisms of photosynthesis, involving light absorption by chlorophyll and associated pigments, followed by electron transfer chains driving carbon fixation, display remarkable efficiency in energy conversion and have inspired attempts to develop artificial photosynthetic systems. Circadian rhythms, the approximately 24-hour cycles in physiology and behavior found in organisms from cyanobacteria to humans, depend on light as the primary synchronizing signal linking internal biological clocks to the external day-night cycle. The molecular mechanisms of circadian timing involve feedback loops of gene expression that generate oscillations, while specialized photoreceptor systems detect light levels and adjust clock phase accordingly. The health implications of circadian disruption, including effects on metabolic function, immune response, and cognitive performance, have received increasing attention as artificial lighting and electronic devices extend light exposure beyond natural patterns. The evolution of circadian systems presumably reflected the adaptive value of anticipating rather than merely responding to daily environmental changes, and the near universality of such systems across diverse organisms suggests ancient evolutionary origins. The visual systems of animals display remarkable diversity in both structure and function, reflecting evolutionary adaptation to different ecological niches and the visual requirements they impose. Compound eyes in insects and some other arthropods provide different performance characteristics than the camera-type eyes of vertebrates and cephalopods, with compound eyes excelling at motion detection and offering panoramic fields of view while camera eyes provide superior spatial resolution. The parallel evolution of camera-type eyes in vertebrates and cephalopods represents a striking example of convergent evolution, with fundamentally similar optical designs arising independently in lineages that had diverged hundreds of millions of years earlier. Color vision varies dramatically across species, with some animals perceiving ultraviolet or infrared wavelengths invisible to humans, while others possess only dichromatic or monochromatic vision, and these differences reflect the spectral properties of relevant environments and the visual tasks that provide selective advantage. The psychological and neurological study of human vision revealed the extraordinary processing occurring between the formation of retinal images and conscious visual perception, with much of this processing inaccessible to introspection. The distinction between sensation, the physical stimulation of sensory receptors, and perception, the constructed experience emerging from neural processing, became increasingly clear through investigations of illusions, attention, and visual deficits resulting from brain damage. The ventral and dorsal visual processing streams, distinguished by Milner and Goodale and others, suggest that visual information serves different functions through separate neural pathways, with implications for understanding both normal vision and the specific deficits resulting from different types of brain injury. The remarkable extent to which visual perception involves construction, rather than simple recording, has implications for understanding eyewitness testimony, artistic representation, and the relationship between appearance and reality. The cultural and symbolic significance of light across human societies extends beyond its practical utility to encompass religious, aesthetic, and philosophical dimensions that resist reduction to merely functional terms. The association of light with knowledge, truth, and goodness appears across diverse cultural traditions with sufficient frequency to suggest something about fundamental cognitive or perceptual associations, while darkness correspondingly carries associations with ignorance, evil, and danger. Architectural traditions in many cultures have emphasized the manipulation of light, whether through orientation toward solar events, the construction of windows and apertures, or the use of reflective surfaces and artificial illumination to create specific effects. The development of photography and cinema created new art forms fundamentally dependent on light capture and manipulation, transforming visual culture and practices of memory and documentation. Artificial lighting's effects on ecology and ecosystems have received increasing attention as the global extent of light pollution expanded through the 20th and 21st centuries, with documented impacts on organisms ranging from insects to birds to mammals including humans. The attraction of insects to artificial lights, sometimes termed phototaxis, results in mortality at individual lights and potentially affects population dynamics and ecosystem services including pollination. Migratory birds navigating by stellar cues experience disorientation near strongly lit urban areas, sometimes resulting in fatal collisions with illuminated buildings, and various mitigation strategies have been developed, though implementation remains inconsistent. The suppression of melatonin production by artificial light exposure at night affects not only sleep quality, but potentially contributes to chronic disease risk, and public health attention to light exposure patterns has increased accordingly. The development of light-emitting diodes represented a technological transition in illumination that combined the efficiency advantages of semiconductor-based light generation with the controllability and form factor flexibility enabled by solid-state devices. Early LEDs produced only low-intensity monochromatic light and found initial applications in indicator lights and digital displays, but the development of high-brightness LEDs capable of white light emission through phosphor conversion opened possibilities for general illumination. the efficiency of LED lighting, measured in lumens per watt, has improved dramatically and now substantially exceeds both incandescent and fluorescent technologies, contributing to reduced energy consumption for equivalent light output. The environmental implications of the transition to LED lighting include reduced electricity demand and associated emissions, though the manufacture and disposal of electronic devices carries its own environmental considerations. Contemporary research in photonics encompasses applications from computing to medicine to communications, with the manipulation of light at various scales, enabling capabilities that continue to expand. Optical computing approaches seek to exploit the speed and parallelism potentially available through photonic rather than electronic information processing, though practical general-purpose optical computers remain elusive. Photodynamic therapy uses light activation of photosensitizing compounds for targeted destruction of abnormal tissue, with applications in cancer treatment and other medical contexts. The field of optogenetics, developed primarily since the 2000s, uses light to control genetically modified neurons expressing light-sensitive proteins, providing unprecedented precision in investigating neural circuit function. The detection of gravitational waves, first accomplished in 2015 by the LIGO collaboration, used laser interferometry at the limits of precision measurement to detect the minute spacetime distortions produced by cataclysmic astronomical events. The interferometer design, in which laser beams travel along perpendicular arms and recombine to detect path length differences, required control of noise sources to extraordinary precision, with the detected signals representing changes in arm length smaller than the diameter of a proton. The detection confirmed a major prediction of general relativity and opened a new observational window onto phenomena including black hole and neutron star mergers that were previously inaccessible to electromagnetic observation. The subsequent development of multi-messenger astronomy, combining gravitational wave and electromagnetic observations, illustrated how different types of radiation could provide complementary information about astrophysical events. The study of light in cosmological context reveals information about the structure and evolution of the universe that cannot be obtained through any other means, with observations across the electromagnetic spectrum contributing to the development of contemporary cosmological models. The cosmic microwave background radiation, discovered in 1965 and subsequently mapped with increasing precision, represents light from the early universe that has been redshifted into the microwave region by cosmic expansion, and its properties constrain models of the universe's composition and early evolution. The accelerating expansion of the universe, inferred from observations of distant supernovae that appear fainter than expected for their redshifts, implies the presence of dark energy with properties that remain poorly understood despite intensive theoretical and observational effort. The use of gravitational lensing, in which light paths are bent by intervening mass distributions, provides information about both the lensing mass and the lensed background sources, contributing to understanding of dark matter distribution. The practical and theoretical investigations of light continue to reveal unexpected phenomena and enable new capabilities, with no indication that fundamental understanding or technological application approaches any final limit. Metamaterials with electromagnetic properties not found in nature, including negative refractive index, have been developed and demonstrated, enabling effects including cloaking and superlenses that exceed classical optical resolution limits. The manipulation of individual photons for quantum information applications, including quantum cryptography and potentially quantum computing, exploits the fundamental quantum properties of light for practical purposes. The detection of biosignatures in exoplanet atmospheres through spectroscopic analysis of starlight passing through those atmospheres represents an application of optical techniques to perhaps the most profound question about the distribution of life in the universe. The integration of understanding across these diverse domains, from fundamental physics through biology to technology and culture, reveals light as a subject that resists containment within any single disciplinary framework, requiring instead approaches that respect both the unity of the underlying physical phenomena and the diversity of their manifestations and implications. The history of light's investigation demonstrates both the cumulative progress possible through systematic inquiry and the recurrence of fundamental questions that require periodic reconceptualization rather than merely additional data. The the contemporary situation in which quantum field theory provides extraordinarily precise predictions, while interpretive questions about the nature of light and electromagnetic phenomena remain contested, recalls earlier periods when predictive success coexisted with conceptual uncertainty, suggesting that the relationship between knowing how to calculate and knowing what exists is less straightforward than sometimes assumed. The economic history of illumination technology reveals patterns of innovation, adoption, and displacement that parallel developments in other technological domains, while displaying distinctive features reflecting light's particular role in human activity. The capital intensity of successive lighting systems, from the distributed production of candles and oil to the infrastructure requirements of gas and electricity, shaped industrial organization and regulatory frameworks in ways that persisted beyond the specific technologies that generated them. The relationship between lighting costs and labor patterns, with cheaper and more abundant illumination, enabling extended work hours and new forms of economic activity, illustrates how infrastructural changes create possibilities that social and economic forces then exploit in ways not determined by the technology itself. The current transition toward LED illumination and smart lighting systems continues these patterns while introducing new elements, including network connectivity and data collection capabilities. The global distribution of artificial lighting, visible from orbit and mappable through satellite observation, correlates with economic development and urbanization while also reflecting historical patterns of infrastructure investment and policy choices. The stark contrast between brightly illuminated regions of North America, Europe, and East Asia, and the relative darkness of much of Africa and South Asia, reveals disparities in energy infrastructure that have implications far beyond illumination itself. The aspiration toward universal energy access, including electric lighting, represents both a development priority and a climate challenge, with the environmental sustainability of continued lighting expansion dependent on the efficiency and carbon intensity of generating technologies. The choice of lighting technologies for areas currently without reliable electricity carries long-term implications, with the availability of solar-powered LED systems potentially enabling leapfrogging past centralized grid infrastructure. The physiological effects of light exposure patterns, characteristic of contemporary urban and indoor lifestyles, differ substantially from those that prevailed through most of human evolutionary history, when artificial lighting was weak and limited, and the health implications of this difference are subjects of ongoing research. The suppression of melatonin by evening light exposure, particularly light in the blue wavelength range emitted by electronic screens and many LED sources, disrupts circadian timing with potential consequences for sleep, metabolism, and longer-term health outcomes. The reduction in bright daylight exposure resulting from predominantly indoor lifestyles may contribute to conditions including myopia, whose increasing prevalence correlates with educational intensity and reduced outdoor time in childhood. The design of built environments and lighting systems with attention to circadian health represents an emerging priority, though implementation remains uneven and the optimal parameters for different populations and purposes continue to be investigated. The philosophical questions raised by light extend from ancient problems about the nature of perception and reality to contemporary debates about the interpretation of quantum mechanics and the relationship between mathematical formalism and physical existence. The fact that human beings have no direct perception of most of the electromagnetic spectrum, knowing of radio waves, X-rays, and other radiations only through instruments and inferences, raises questions about the relationship between perception and reality that parallel concerns expressed in traditions from Plato to neuroscience about the constructed character of conscious experience. The quantum mechanical treatment of light as neither purely wave nor purely particle, but as something requiring a fundamentally new conceptual framework, has implications beyond physics for understanding how scientific concepts relate to everyday intuitions, and whether the latter set limits on the former. The ongoing debates about the interpretation of quantum mechanics, including questions about measurement, observation, and the role of conscious observers, frequently center on light-related phenomena, including the double-slit experiment and various interferometric setups. The aesthetic appreciation of light, from natural phenomena through artistic manipulation, to the designed illumination of architecture and public spaces, reveals dimensions of human response to light that exceed functional requirements, while reflecting both biological and cultural factors. The emotional responses evoked by different lighting conditions, including preferences for certain color temperatures, intensity levels, and distributions, show both individual variation and cultural patterns that complicate purely functionalist approaches to lighting design. The history of painting's engagement with light representation, from chiaroscuro techniques through Impressionism's attention to outdoor light effects to contemporary explorations using light itself as artistic medium, traces an ongoing investigation of perception and representation. The professional development of lighting design as a distinct field, with specialized education and practice standards, reflects the growing recognition that light manipulation constitutes a design domain with its own requirements and possibilities. The investigation of light throughout human history illustrates how a phenomenon of everyday experience can simultaneously drive practical innovation and provoke fundamental questions about the nature of reality, with progress in one dimension not necessarily resolving difficulties in the other. The confidence of late 19th century physics that light was well understood as electromagnetic waves propagating through the ether gave way to the revolutionary developments of the 20th century, suggesting that apparent completeness of understanding can be misleading. Contemporary physics achieves extraordinary predictive precision while leaving interpretive questions unresolved, a situation that might be viewed either as demonstrating the limits of understanding or as indicating that certain questions are poorly posed or practically unanswerable. The continuing development of technologies exploiting light's properties proceeds somewhat independently of these foundational debates, illustrating how practical capability and theoretical understanding can develop along partially independent paths. The future development of light-related science and technology remains as unpredictable as past developments would have appeared from earlier perspectives, though certain directions seem indicated by current research trajectories. The continued improvement of solar energy conversion efficiency and cost reduction could substantially affect global energy systems and by extension illuminate economic and geopolitical patterns, though the rate and extent of such developments remain uncertain. The application of optical techniques to biological and medical contexts, including imaging, diagnosis, and therapy, continues to expand capabilities with potential health implications that are difficult to forecast. The development of optical computing, quantum communication, and other advanced applications depends on solving technical challenges whose difficulty is uncertain and whose eventual solutions may differ from current expectations. Throughout this account, the attempt has been to trace causal relationships and structural factors, rather than merely cataloguing discoveries and inventions, to understand developments within the conceptual and practical context that shaped them, rather than evaluating them retrospectively by later standards, and to indicate where uncertainty, controversy, and ongoing investigation characterize the current state of understanding, rather than presenting a falsely definitive picture. Light has served as a thread connecting investigations across domains from fundamental physics to industrial technology to human physiology to cultural expression, revealing both the unity of the underlying phenomena and the diversity of perspectives and purposes that have shaped human engagement with illumination across millennia. The story is far from complete, with current research and future developments certain to extend and revise current understanding in ways that cannot be fully anticipated, continuing a process of investigation that extends back to the earliest recorded human inquiry and shows no sign of approaching any final resolution.